Hey again, everyone. This is the second lecture for Chapter 2. And in this lecture, we're going to talk about acceleration and derive what are called kinematic equations. So just again, real quick, let me look at the textbook. And so I will share the screen here, and we will go again into Wiley Plus, or sorry, into Canvas and go to Wiley Course Resources. And you might have seen here real quick that there is a new module or a module for chapter 2. But let's look at the textbook, going back to chapter 2. And I think I'll look at the table of contents first real quick. So chapter 2, again, last time we talked about position, displacement, and average velocity. We talked a little bit about instantaneous velocity and speed. We're going to talk about acceleration and actually do some derivatives because that's how we get the slope and get instantaneous velocities, things like that. And then we're going to talk about constant acceleration and derive what are called kinematic equations. So let me go ahead and start by just reviewing what we defined last time. So going back here, position, displacement, and average velocity, right? We define displacement. So delta x here is x2 minus x1, or as I call it, x final minus x initial. Average velocity is your change in x over your change in time, right? And your instantaneous velocity is going to be the slope at any moment in time. So if you look at some of the stuff in the book here, right, your slope might change. So this is a position versus time graph. You might see you're going fastest here where the slope is biggest. It's kind of slowing down in this region. Okay, so just to remind you, again, looking at the book is a good idea, but hopefully I hit the high points of all of this. So we're going to go now to looking at what is the definition of acceleration. All right, and you can see it here, but I'm going to go ahead and write stuff down. So let me share my camera. And so just to remind you again, last time we defined our velocity to be delta x over delta t. And this is in units of meters per second in the metric system or the SI system. Right? It's basically a distance or a length over a time. When you have a constant velocity, what I would say is there is zero acceleration. So basically, the acceleration is the rate of change of the velocity. You have to have a changing velocity, right? And it gets a little tricky, it gets a little confusing because they seem quite similar. But let me write down our definition of average acceleration. I'm going to call it A, and it's going to be delta V over delta T, right? So it's a change in velocity over a change in time. So I will have a V final or a V2 minus a V initial or V1 over that time change, okay? So just as a quick example, let's say that your V initial was 5 meters per second and your V final was negative 10 meters per second. And you made this change in a time of 2 seconds, right? So what's happening here? Well, you're starting with a positive velocity and then ending with a negative velocity. So what has actually happened is you have turned around and are now going the opposite direction. Because remember, the negative sign is telling me the direction is to the left. This means that the velocity actually had to go through zero. And just like for average velocity, this is going to be, if I use the calculation for acceleration, I'm going to get an average acceleration, right? Because I could slow down really fast and then speed back up slowly. There could be a number of ways that I could change my velocity from 5 to negative 10 in that 2-second period. But if I do the calculation, I have my V final, which is negative 10 meters per second, minus my positive 5 that I started with over 2 seconds. So this is negative 15 meters per second over 2 seconds. So that is negative 7.5. Now let's look at the units. The units are meters per second divided by seconds. Oftentimes people will write this as meters per second squared. But really what it means is meters per second per second. My speed has been changing by negative 7.5 meters per second each second, right, on average. Now, acceleration is a vector. In this case, I would say my acceleration is pointed in the negative direction, or maybe the left, if that's your coordinate axis. What it is saying is I am subtracting 7.5 meters per second every second. Now, as I'm moving forward, I'm slowing down until I get to 0, but my acceleration is still in the negative direction. So once I hit 0 velocity, I am going to speed up and go the other way. So hopefully that makes sense, right? The acceleration is negative. And so if I were to assume that, let's say I had a constant acceleration, what would my velocity versus time graph look like? All right, so let's draw that here. So maybe I'm going to start at 5 meters per second, and I'm going to end up at negative 10. So down here in my negative region. So what it's saying is that time equals 0. So here's 1 second, and we'll go to 2 seconds. At time equals 0, I am starting at 5 meters per second. At time equals 2, I'm down at negative 10. Now, if I were going at a constant acceleration, I would have a negative constant slope, right? Because similar to the displacement or the position graph versus velocity, the acceleration is the slope of the velocity graph, right? So this is delta V over delta T. I'm getting a negative slope because my acceleration is in that negative direction. But notice, in this region, I still have a positive velocity, right? I'm going forward, but I'm just slowing down. Once I cross the time axis, my velocity instantaneously, just at that moment, is 0 as I come to a stop and I'm turning around. As I turn around, my velocity is becoming more and more negative. So I'm actually speeding up in the negative direction. Okay, so this is also, this is a case of constant acceleration. Once again, you could have a situation where your acceleration was different. Maybe you took a different acceleration path to get from 0 seconds to 2 seconds. I'm not going to go through all the details of that. It's kind of similar to the velocity and position graph, right? But the thing to remember is that the acceleration is the slope of the velocity graph. So just real quick, constant acceleration is a really important thing. And in fact, we are going to derive something called kinematic equations here in just a second. But let's just look at our constant acceleration. So I'm going to call it constant A. If I have a constant acceleration, let's make our graphs here. So my acceleration versus time graph, say we have a positive acceleration. If it's constant, it's just a straight line, right? I am just going at whatever meters per second squared I have. Now my velocity graph, if I have a constant acceleration, what does that mean? Let's say that our acceleration was, we'll say 2 meters per second squared. It's a constant. It means the slope of my velocity graph is 2 meters per second every second. So it's going to be a straight line with a positive slope in this case. Again, if my acceleration were negative, it would be a negative slope. But the slope is equal to the acceleration, right? So my velocity is getting bigger and bigger. I have a positive acceleration. It means that my velocity is going up by that 2 meters per second every second. All right. Now let's look, what about the position versus time graph? Now this is going to be different. It's not going to be a straight line because as we know, the position graph, the slope of the position graph is the velocity, and that is changing. The slope is changing. So I'm going to start out with maybe a position, we'll call it, say, I mean, I could start at whatever position, but let's say we start at 0. I'm going to have a pretty slow velocity. But as time goes on, the slope is going to get bigger. And so I'm going to have a graph that kind of curves with time because, right, at each instantaneous moment in time, the slope is equal to my velocity, and it's getting bigger and bigger as time goes on. As we'll see, this is actually a parabola. And if you remember, a parabola is a quadratic relation. So x is going to be proportional to the time squared. Now here, if you have a straight line, right, that's a linear relation, and velocity would be proportional to the time. So that's kind of a description of constant acceleration. And constant acceleration is going to be very important in what we're going to study. In fact, we're going to do a lot of problems with constant acceleration for a couple reasons. One reason is that constant acceleration is easier to deal with, right? You have a constant acceleration, you can easily get some equations for the velocity as a function of time and for position as a function of time. We just need to know what that acceleration is. And that's what we're going to do next. We're going to get these kinematic equations, which are for constant accelerations. But the other reason is that it is important. It happens a lot in nature. In fact, one of the problems we'll look at in our next lecture is what if I drop a ball or a rock or an object near the Earth? Well, it tends to have a constant acceleration. And it turns out that acceleration due to gravity is about negative 9.8 meters per second squared. Once I know that acceleration, I can use these definitions to actually determine what is the velocity after 5 seconds or 3 seconds. Where is it? What is its position? And so this is the importance, right? Once I know the acceleration is constant, I can figure out what the position is, where it is, and how fast it's going at any later time. And so that is our next goal. Using our definitions, can we determine relationships between acceleration, velocity, position, and time, right? All of these things are going to depend on time. Now, before I do that, though, I want to point out, again, that we always won't have a constant acceleration. And I want to do a little bit of calculus here. When we're talking about instantaneous values, sometimes we don't have this. But we may have a function of time given to us. So let's say our position as a function of time might be, let's say, 5t cubed minus t squared plus 3. All right, so that's telling us the position at any time. What is the velocity? Well, my instantaneous velocity function at any time is just dx dt. All right, so maybe you've seen this in your calculus class. To get the velocity, right, it's just the slope of the position. So I just take the derivative. And so what I would get, I'm going to bring my 3 down. I'm going to get 15t squared minus 2t. Okay. Now, that will give me the speed in meters per second, or the velocity in meters per second at any time. But what about acceleration? Well, it's dv dt, right? Again, acceleration is the slope of the velocity graph. Or I could say that it's the second derivative of the position, d squared x dt squared. So I just take another derivative, and I'm going to get 30t minus 2. Now notice, this is not a constant acceleration. In fact, the acceleration is getting faster and faster, or a bit more and more every second. So not only will my velocity not change at a linear rate, but you can see my x of t is not a quadratic relation. I have to have a t squared as the highest power in my position if I'm going to get a constant acceleration so that I don't end up with a t down here in that acceleration function. Okay. So we could use calculus to derive the equations for a constant acceleration, but I'm going to go ahead and do it a different way. And then maybe in the next lecture, we could use calculus a little more. It involves some integral calculus, but let's go ahead and look at our kinematic equations. So again, what do I mean by kinematic equations? These only apply when your acceleration is constant, when a is constant. But kind of why they're called kinematic equations is because they will tell me what the motion is like. Once I know that constant acceleration, I can tell you where the object is, its position, and its velocity. Now, the first one we can kind of get from our definition of acceleration, right? Delta v over delta t. Remember that delta v is v final minus v initial. And instead of writing delta t, I'm just going to write t. I'm going to, I can always choose my origin of time to be 0. So my t initial is just 0. So after whatever time. So let's rearrange this. So I'm going to solve for v final. If I do that, just a little bit of algebra, I get v final is a times t minus or plus vi. So vi plus at. This is our first kinematic equation. And it tells us, okay, let's say I know 3 quantities. I know the 3 quantities: initial velocity, acceleration, and time. I can tell you what the final velocity is. Now, by final velocity, what I mean is whatever velocity at that time I'm looking at, right? Whatever time I choose. So really, I could write this as v of t is equal to v initial plus at. Sometimes you'll see these kinematic equations written a little differently. You might, instead of vi, people might use v0 or v naught for time equals 0. So just be aware that I may write them in a certain way, but they could be written in the book or in other places a little bit differently. So this gives us our first kinematic equation. The problem here, I want to get other relation with other quantities. In fact, what I would like to get is the displacement, right? How do I know what the displacement is, right? So delta x, how is it related to these other quantities, initial velocity, time? It's a little easier to show this directly with calculus, but let me kind of do an argument here. If you had a constant speed, if my velocity is constant, my speed is constant, my acceleration would be 0, right? But it's still a constant acceleration, it's just 0. Well, my delta x, my displacement, would just be the velocity times the time. So in the case when there's no acceleration, this makes sense. This is what you do, right? If you're going at 10 meters per second and you go for a time of 2 seconds, you just take the 10 meters per second times the 2, you've covered 20 meters. That's pretty straightforward. But the question then is, well, what if I'm accelerating? When I'm accelerating, my velocity is not constant anymore, right? It's going up. I'm going to cover more distance, more displacement at later times as my velocity gets faster and faster. I'm going to argue that for the case when acceleration is not 0, right, when I don't have a constant velocity, that I can do this. I can use an average velocity. And by average velocity, I just mean I'm going to take v initial plus v final and divide by 2. It's kind of like averaging 2 exam scores, right? I add them together and divide by the number of the scores. So there, and the reason that this does not work if the acceleration is not constant. If the acceleration is constant though, and it's not equal to 0, I can use this. And it makes sense because if I have a constant acceleration, half the time I'm above the average value, right, for my velocity, the other half I'm below. So the average is right in the middle. It's the average, actual statistical average of the two numbers, initial and final. So this is our second kinematic equation. And again, you might see it written different ways. In fact, right, delta x is really x final minus x initial. So I might write it like this. Some people will use x0. So I could also write it like this. X of t is x0, right? I'm bringing the x initial over, plus v0 plus v over 2, right? V is my final velocity at whatever time. The point is, I may write it in different ways, but just remember how displacement and initial and final velocities are related. I'm going to typically write it like this because that's what I'm used to. But again, you will see it written different ways. So at this point, we have these two kinematic equations. Let me just write them down. So V final equals V initial plus AT, and our displacement, right, which is x final minus x initial, is our average velocity, V initial plus V final over 2 times t. Now, one of the things about these equations are that they both include the final velocity, which is typically not something we know to begin with. If I'm talking about the motion of a car, I would know what speed it started with or what velocity it started with, but I don't necessarily know how fast it's going later on. So I would like to get another equation. I would like to get an equation that doesn't have V final in it. Well, that's pretty easy to do from these two equations. All I have to do is do a little algebra. I can plug this expression for V initial plus AT into here, right? Just substitute V initial plus AT in there, do a little bit of algebra, and what I end up getting is this third kinematic equation. Now, I'm not going to work through the algebra. I'm going to leave that as an exercise for you if you want, but I'm just doing substitution and rearranging. And what I end up getting is my displacement is V initial times t plus 1/2 AT squared. And again, delta x is x final minus x initial, right? It's related to position. So here you can see the thing that I just said previously, I have a quadratic or parabolic relation between my position and my time, right? So this is only going to happen for a constant acceleration. All right, so these equations we could use to solve problems. For example, if I know my initial speed, my acceleration, and my time, I could figure out what displacement or what position the object was at any later time. I'm going to write down one last equation for these kinematic equations that doesn't have the time, because there can be problems where we don't know right offhand the time. As it will turn out, I could always solve for the time from one of the equations and use another one to get whatever other quantity I'm looking for. But let me write down the last kinematic equation. And the way this is obtained is just by some algebra, right? I could solve for t from this equation and plug it into here, do some more manipulations. I'm not going to go through all those. What you end up getting is V final squared equals V initial squared plus 2a times delta x times the displacement. So these four equations are what I call our kinematic equations. Right? In the next lecture, we're going to do some examples. I just wanted to derive them here and talk about the relation between acceleration, velocity, and displacement or position. So I'm going to stop there. In the next lecture, again, we'll do some examples.